Hello everyone. Welcome to today's helping and discussion session. Uh, I'm taking this basic real analysis uh, tutorial sessions to help learners. Um, so if you have any question, you want to discuss a problem or concept, you can uh, ask me. Uh, I have prepared some material to discuss with you. Uh, so in that material also, if you find any difficulty understanding any argument that I give, you can immediately ask. Don't feel hesitate uh, to respond. Okay, so I expect you to respond. Okay, so without a further ado, we can start now. So let me formally introduce myself. I'm Prerak, and I'm from Aizer Bhopal, and I'm conducting these discussion session with you uh, weekly, Monday from 7 to 9. And this is a 2 hour live session, and recording of these discussion sessions will be available on the YouTube channel, which is named Maths with Prerak Deep. You can go to this YouTube channel. You can find this recording. You will be able to find this recording by tomorrow morning, and you can find other recordings, my previous sessions recording, uh, on that YouTube channel if you go now. Uh, yeah. So let's move on to discuss some questions on limit of sequences. So some exercise on limit limit of sequences and functions. Okay. Yeah. So before doing this question 1.1, let me discuss a question which is on limit of sequences. So I hope all of you are familiar with sequences. I'm not gonna go back to the definition of sequence. So in this question, you need to find out the limit of sequence, and the sequence can be easily be found out to be this. Okay, for each and in the natural number set. So this is my sequence. Okay, and I need to find out the limit of this sequence. Limit of an. Okay, uh, and the claim is that this limit is going to be equal to 0, which is I need to show. So what do we mean when I say limit of a sequence? I mean that uh, as n tends to infinity, what happens to uh, as n tends to infinity? Where does this value an tends to? Okay, where does it tends to? This is what the limiting of a sequence mean. Okay, limit of a sequence an. So in this case, it is already given that this sequence is limiting to 0. Okay, you just only need to prove that a limit of this sequence a is 0. Okay, so how do we do that? uh, so let us recall how we used to find limit of a sequence. So we say uh, for any epsilon greater than 0, there exists a natural number n such that an minus a modulus of that is smaller than 0 for all n larger than larger than capital N. Okay, then we say sequence an converges to a as n tends to infinity. Okay, so this is the definition of limit of a sequence. Is this definition fine with you? Okay. Um, so what do we have in this case? So you have a and to be given by n square plus 1 minus n. A is given to be 0. Okay. So what you need to find out? You need to find out n, a natural number n, such that n square plus 1 minus n minus 0, which is nothing but this, is smaller than epsilon for all n greater than n. Okay, you need to find out this value. Okay, so how do we do that? So let's go back to the sequence. So you have this sequence given, which is an equal to n square plus 1 square root minus n. So we modify this sequence a bit, uh, because you can notice over here that we are having n in the uh, so we are having n as the numerator, and the denominator is 1, if you can think of it as a fractional sequence. So in this case, it feels like you cannot bound this sequence by something you know already. Okay, so the idea of sequence convergence is always to bound a sequence with some sequence which you already know. Okay, so in this case, it feels like it doesn't. You cannot bound it with something you know already, because this n square is on the top. Usually, if n is on in the denominator, we it that gives you the bound on the sequence. Okay, which is not the case in this. Uh, so it feels like, uh, as I go, as n tends to infinity, this value also tends to a larger value. It doesn't get bound by some epsilon. That's what I meant. Okay, so first we try to reduce this expression into something which looks like can be bound by something. So how do we do that? We multiply this with divided by this n square plus 1. We multiply with this factor. What do we get? We will get n square plus 1 minus n square, sorry, plus over here, minus n square. So this is a formula for a minus b, a plus b. Okay, so we will get this thing. Okay, so finding limit of, so an, now we have uh, now this now we have written down another expression for an. So these two expressions are same. These two expressions are same. So finding limit of an as n tends to infinity is equal to finding limit of this expression which we have just reduced. Now we can further simplify this expression, because minus n square gets cancel out and we get 1 on the top, and the denominator is just this thing. So we get this expression that 1 divided by n square plus 1 my plus n. Okay, so now this whole thing is in the denominator. So it feels like we can bound it as n tends to infinity. It is bounded because the denominator will also go to 0 as this thing. So the denominator will goes to infinity. So this whole fraction will go to 0 as n tends to infinity. It gives you the confidence to say that. Now we need to find the appropriate bound to this. Okay, so now a question. Now we know that the question was that limit of an was 0. So limit of this sequence is 0. So now question has changed to this thing, that you need to find out that limit of n tends to infinity of this sequence is equal to 0. Okay, Now again we use the definition of limit of a sequence. So we start with some epsilon, epsilon be greater than 0. Now we need to find out n in natural number set such that 1 minus n square plus 1 square root plus n is smaller than epsilon for all n greater than n. Okay, so how do we do that? So you need to notice over here that this term, okay, so you need to notice here that this n square plus n is larger than, okay, if I, okay, let me write it in this way, n square plus 1 is smaller than n square plus 1 plus n. Why? Because you are adding some positive quantity to this value, so it has to be larger than this. Okay, so what does this imply? This says that 1 over n square plus 1 plus n is smaller than 1 over this thing. Okay, is this fine? This reduction is fine?
Yes, sir.
Okay. So, um, so now what do we have? So if this is fine, then you further reduce it, that n square plus 1, n square root. Okay, so do it in this way. N square is smaller than n square plus 1. Okay, so if I take the square root, this is also smaller than this, because square root is a increasing function. Okay, so this happens. That means 1 over n square plus 1 is smaller than 1 over n square. Now what is 1 over square root of n square? It is 1 over n. Okay, so now this is your first inequality, this is your second inequality. Now from A and B, what will you get? You will get that 1 over n square plus 1 plus n is smaller than 1 over n. Okay, so now you know, so you get this inequality. Okay, let's call this star. Now we know that limit of n tends to infinity of 1 over n is 0. We know that already. We can use it as a fact now. So for given epsilon, so the epsilon that you started with, this epsilon, so there will be some n for this epsilon, there will be some n for this sequence. Okay, so let me say we know that this happens. So for epsilon greater than 0, there is n in natural number such that 1 over n minus 0, this modulus is smaller than epsilon for all n greater than n, which is same as 1 over n is smaller than epsilon. Okay, so now we come back to this part. Okay, so we come back to this part. So the modulus then, the modulus of n square plus 1 plus n, this modulus will be smaller than modulus of this, and which is smaller than epsilon. Okay, which is smaller than epsilon. So what is n in this case? So n in this case is the same n that we got for this sequence. Okay. So this implies that the limit of an is equal to 0 as n tends to infinity. Okay, so this completes the proof of the question. So let me pause for a few minutes, up for a few seconds. So is this a question fine with everyone? Has Have you understood the argument? How do we say it? Any doubt? Anyone? Okay. If this question is fine, we can move on to discuss uh, the limit of functions. Okay. So what we were discussing just now, we were discussing the limit of a sequences. Now we have a limit. Now we need to find out the limit of a sequence. Sorry, of a function now. So now we have function instead of sequence. So each of the in each of the question we have function of real variable to uh, real value. So we have functions from R to R. Okay. So we have function from R to R, and we want to find out the limit of function fx as x tends to some value a. Okay. So what do we mean by that? Let me say the definition formally. So definition goes as follow. So we say a function f from R to R has a limit at as at a if for every epsilon greater than 0 there exists delta greater than 0 such that fx minus fa is smaller than epsilon for every x whose distance from a is smaller than delta. Okay, so this is the definition of a function having a limit at a. Sorry, uh, okay. So we say a function f has a limit at a. Uh, function has a limit at a for every epsilon. Limit b at a. So that will be more appropriate. Limit b at a. Okay, limit b at a if for every epsilon there exists some delta such that this thing happens. Okay. Okay, so how do we see this definition in reality? So we so let me draw some geometry. So let me give you some geometric intuition to that. um, so this is my x-axis. Okay, and this is my y-axis. Now this is my x-axis, this is my y-axis. So whenever I have a function from real value to real value, I can always draw this function. So I can always draw this function as a graph in R2. So a function can be drawn as a graph x comma fx, as a curve, basically as a curve in R2. Okay, so that's what we call the graph of the function. So what do we mean by that? For example, if you have function which is like fx is equal to 1 for all x in R, this is your function, then this function will look like this. Okay, this is your fx. And if you have function which is like fx equal to, sorry, my bad, equal to sine x for x in R. So this sine x function, a more easier function, let's take x only. Okay, so function is your fx is equal to x. So this function will look like um fx equal to x. So this function will look like this. Yeah. So this will be the function. Okay. So I hope you get the idea. Now, what is this limit of function means? So it says that we say a function. Let's say this is the point where I am finding out the limit. This is a. Okay. So I am looking at the neighborhood of this a point, a small enough neighborhood. Okay, of radius delta, and so what we are looking at, so we are looking at the value of the function. Okay, so let's say this is b, this is b. Okay, this is b, and now what you're doing, so for any given neighborhood of b, okay, so for any given neighborhood of b, which we are taking in this case to be the epsilon radius, sorry, the epsilon radius. So this is epsilon radius neighborhood. Okay, so in particular this thing. Okay, so for any given epsilon you need to find out a delta. Okay, you need to find out a delta for which, if you take any um, if you take any uh, sorry, for you need to find out a delta such that delta radius neighborhood at a, which is this. Okay, delta radius neighborhood at a. Okay, if you take any point in this delta radius neighborhood, its corresponding function value will lie in this neighborhood, in this epsilon neighborhood of b. Okay, So if you take any x in this delta neighborhood, then its corresponding function value lie in this epsilon neighborhood. Okay, so how can we write it? So this similar thing can be write it as, so for a given epsilon, you need to find out some delta. So there exists a delta such that fx minus f fx minus b smaller than epsilon whenever x minus a smaller than delta. Okay, so whenever this x lies in the delta neighborhood of a, your function value corresponding to that x need to lie in the epsilon radius neighborhood of b. Okay, so this is what I'm written over here. It is equivalent to say in this way, and that's what the limit of a function means. Okay, so v is the value. uh, so your function is tending to that b as x tending to a. So as x is going towards a, um your function fx is tending to b. Okay, so yeah, so in case of example, for example, in case of fx equal to x, uh, if you say your a is, let's say for example, if you take for example, if a is your 1 and f is your fx is your x. Okay, so uh, as x tends to 1, your function value will also tends to 1 because it's the same function. So it will be b will be 1 in that case. Okay, let's move on to solving these questions, so it will be much easier for you. So okay, now let's discuss the first question. So part a. So part a says you need to find out limit of x tends to 1, x plus 1, 2x plus 3. No, that delta will not be unique in that case uh, because any smaller delta will also satisfy this condition. So you need to find out in some sense the maximum delta for which this thing happens. You need to just say that there exists a delta. Okay, it doesn't say that the delta has to be unique. You just need to find out a delta for which these two inequalities are satisfied. Your function value lies in that epsilon neighborhood. Okay, that delta is not unique. Okay. So now we need to find out the limit of these functions. How do we do that? So we use some fact over here. Okay, so facts are what are those facts? So fact number one is that uh, if limit of fx as x tends to a and limit of gx as x tends to a, and assume that limit of gx is non-zero. Okay, so don't assume that right now. So let's say limit of fx at when x tends to a and limit of gx. Okay, let's say this is v and limit of x tends to a of gx is c, then limit of their product is b times c. Okay, number one fact. Fact number two, limit of fx as x tends to a. Okay, call it b. Limit. Okay, so let make my life easier. So if limit of x tends to a, gx which is c, is non-zero, then you have the formulation for division also. So you can talk about limit of this function. This is going to be v over c. And you can also say, you can also talk about the addition of the limits. So limit of fx plus gx, fx or minus as I tends to a, will be equal to v plus minus c. Okay. Um, yeah. So that's all the fact that I'm gonna use over here in solving these questions. Okay. So in the first part you have x1, x plus 1, you have x 2x plus 3. So we know that limit of individual term exists. So limit of x tends to 1 of x plus 1 is what? It is 2. And how do we prove that? So x plus 1 minus 2 is smaller than epsilon. Yeah, this is smaller than epsilon. So you need to find out as x minus 1 is smaller than delta. So what is this? This is nothing but x minus 1. So you can take delta to be equal to epsilon. Okay. So this proves that the limit of x plus 1 is minus 2. Is 2 actually. Okay. So this is 2. Similarly, limit of x tends to 1 of 2x plus 3 is um, is again going to be, just put this value in this because these are continuous functions which you will learn later on. So linear functions are continuous function which you will learn. I think you have already learned that. So you can just substitute that value in this. So you will get 5. Okay, and you can prove it practically as well. You can use the theory of epsilon delta to prove that. So for example, you take start with epsilon greater than 0. You need to find out delta greater than 0. So this is what you need to find out. How will you do that? You just take this minus 5, which is smaller than epsilon. This is what you need. So for you to find out that x, which will happen. So this, if you solve this equation, you will get minus 2. Okay, and you further solve it, you will get x minus 1, this modulus. So this is smaller than epsilon by 2. So you take this to be your delta. Okay, so now what happens? So whenever this delta is equal to this epsilon by 2, you can go back. Okay, so these are equivalent statements. So this will be your delta in this case. Okay, so now limit of both of the things exists. Now I can use this property number. So let's name them. Let's say this is property number 2. This is property number 3. So I use fact number 3. So by fact number 3, I get the limit of the multiplication of these two linear functions is going to be 10. Sorry, Ravi, I couldn't get your question. Uh, can we do this through epsilon delta method? Yeah, so actually I use the epsilon delta to find out the limit of mm, x plus 1 and x plus 2x plus 3. Okay, and once you know the limit of those two functions independently, you can use these facts. Okay, that addition of two functions, uh, limit of addition of two functions will be the addition of their limits. So that's what, and multiplication of that is again going to be this. So that's what I used over here. So in order to find out the limit of these two functions, I use epsilon delta, and then once I know the limit of these two functions, I can use the fact, and uh, I hope it makes sense. So this is the more appropriate way and more convenient way for you also to do these types of questions. Okay. So first you need to guess what will be the limit of the function. Second, you need to prove that is the limit of the function by finding out delta in terms of epsilon. Okay. And third, when you know both of the limits, you need to use properties of limit of functions to get the answer to your question. Okay. Uh, so there are three steps involved. If you can algorithmic, if you can algorithm it, so there are three steps involved. Okay. So now let's move on to discuss next question. Okay. Oh, okay. Okay. Um, yeah. Now discuss the next question in this only. So B part. So B part is, again we will use the result. So now B part of this question is, to you need to find out the limit of x tends to uh, 2 of this fractional function. This is equal to um, what? So now let's we want to use the fact number 2 in this case. Okay. So how do we use the fact number 2 in this case? You need to say that the limit of the denominator function is non-zero. Okay. So you do that. So how do, first you need to check that whether the limit of both of the functions exist. So this is the limit of this, and limit of x tends to 2, x square minus 2. So now what is x square plus 2? So guess is that limit of this is going to be 4. And now x square plus 2 minus 4. This is smaller than epsilon. You need to find out the appropriate x for which this happens. Okay. So you do that, x square minus 2 this, and now this x square plus x square minus 2,
Sir, sir,
this x square minus 2 is smaller than um, x square minus 1. So x square minus 2, sorry, yeah, it is 6. Thank you. So it will be x square minus 4. Thank you. Correct. So it is x minus 2 times x plus 2, smaller than epsilon we want. And now, yeah, so this whole thing will be smaller than 4 times x minus 2. And now we have x minus 2. X minus 2 will be smaller than x minus 1. Okay, so you want this to be smaller than epsilon. So you take x minus 1 smaller than 1 over 4. You take this to be delta. So what happens? So whenever x minus 1 is smaller than delta, so that means it is smaller than this. This 4 times this thing happens, and it is smaller than, now you just go back to the argument. So yeah, I hope this will work. Epsilon by 4 will work in this case. Okay. So this is continuous. Sorry, so this is limit of this function will be minus 6. You can prove this limit of this function will be 6. That's how you can prove. Similarly, again, you can prove, you can give the same argument for this. It will be 2 again. Okay. Um, yeah, now once you know the limit, so it is non-zero. You can apply this fact number 2 to say that. And now the fact number 2, yeah. So now you use fact number 2 to find out the limit of the fraction. So it will be limit of so it will limit of the numerator and limit of the denominator. So it will be 3. Okay. Now what is the next question? It is limit of this 1 over x plus 1, limit of 1 over 2x. So again, we know that uh, limit of real functions, we know they exist, and what are the value? It is just nothing but this thing. So you can again, so we have already proven in the last part that limit of x plus 1 when x tends to 1 is 2. In this case, it is tending to 0, 2. So okay, let's see that. Let me find out limit of x tends to 2. So case C, limit x tends to 2 of 1 over x plus 1 minus 1 over 2x. Okay. So yeah, and further x is always positive in this case given. So we first, now I know that if limit of this function and limit of this function individually exist, I can break this limit into two parts. Okay, and I can take the difference of their limits by using fact number 3. So first I need to say that does this limit of first sequence exist? Now in order to find out the limit of this sequence, again I apply the fact number 2, which says that the if I have the denominator, if I have 1 over something, I will check the limit for both of the numerator and denominator, and if the denominator doesn't have limit value uh, non-zero, then the limit will exist in this case. So this is if and only if limit of this is non-zero. And now what is the limit of this? Again, the guess is 3. It is limit is 3. um, and how do we prove that it is 3? So we take this thing, and now this is going to be minus 2. Okay, so this is more than x minus 1. Okay, and you can take delta to be, or this is f, yeah, this is x minus 2, which is smaller than epsilon. So you can take, you will just add plus 1 both sides, you will get x minus 1. This will be epsilon plus 1. Okay, this will be your delta. Oh sorry, you just want to have uh, at 2 only, so this is fine. So you can take delta to be this only. So you are done in this case. So delta will be same as this, so the limit will be fine. It is non-zero limit, you can divide. So this limit exists, that means this limit exists, and this limit is going to be 1 over 3. Similarly, a limit of 1 over 2x, it is going to be, as x tends to 2, it is going to be 4, 1 over 4. Okay, and you can again use the fact number uh, 3 to say that limit of their difference is going to be difference of individual limit term. So it will be 1 over 3 minus 1 over 4. Answer will be 1 over 12. Okay. Once used. Once you rational data, once use here rational data. So okay, so for 1 over 2x, I have proven for 1 over 1 plus x, the limit is that. Similarly, 1 for 2x, you can prove. So limit for this will make sense if limit of 2x makes sense. Now limit of 2x is what it is going to be 4. And how do we, this is guess, okay. And now we prove it. So for given epsilon greater than 0, we want that this thing to happen smaller than epsilon whenever x minus 2 is smaller than delta. Okay. So if I start with this inequality, I will take 2 common, I will get this epsilon. So this thing, I will get this. So I will take this as delta. Okay. So whenever so this will hold whenever I take delta to be equal to epsilon by 2. Okay. So this proves that limit of 2x is equal to 4. Hence the limit of 1 over 2x is 1 over 4. Does this make sense? Okay, now let's do question number D. So in question number D, we know the limit of both of the things. Just a minute. X equal to 0. Okay, x tends to 0. So what is this limit? You need to find out. So again, I will use the fact number 2, which is that limit of top, limit of bottom, uh, and then for that I need to say that limit of the denominator must not be equal to 0 as x tends to 0. So x square plus 2, limit of that as x tends to 0 shouldn't be 0, non-zero. Okay. So for epsilon greater than 0, I take this. Uh, so it will be 2. This will be smaller than 0, smaller than epsilon. So x square is being smaller than epsilon, which is same as to say that x smaller than epsilon, modulus of x is smaller than epsilon. Okay, so you can take delta to be epsilon in this case. Okay, so I will leave it this thing. Now you have limit of x plus 1. You know limit of x square plus 2. So this will give you, this is 1 and this is 2. So the limit is half. Any question now? Okay, so we have discussed questions on limit of functions, limit of a sequence also. Let us discuss some more questions for limit of functions. Okay, so I have almost 4 more questions with for you to discuss with you, and then we will move on to discussing some theoretical questions as well, which are part of your assignment. Okay. Okay, so now let's question number 3. So you need to find out the limit of this sequence where x is greater than 0. Okay, so idea here is to use those limiting properties of those limit. So in order to use that over here, as you have seen, that first you need to have that limit of this sequence, sorry, limit of x plus 2x square needs to be non-zero. Okay, but which is not the case, as you can see directly. This is not the case because x plus 2x square, this thing, x plus 2x square, um yeah, x plus 2x square is not is equal to 0 as x tends to 0. Okay, because x is result of that fact number 3. So you need to somehow manipulate this expression of limit in some sense to get what you need. Okay, so um, yeah, so we need to find out limit of this expression 1 plus 3x 1 plus 2x minus 1 plus 3x divided by x plus 2x square. Okay, so since we have so we have a rational function over here, and you have some expression of square root of a plus minus x square root of b type. So we will try to remove the square root in the numerator. Okay, so we will do that by multiplying this function with appropriate square root function with positive sign. Okay, so as we do that, what we will get? We will get so what we will get on the in the numerator? We will get 1 plus 2x minus 1 plus 3x. Okay, I will keep the it will keep the denominator same. So you will get minus x on the top, and you will get, and you can take x from here also. You can take x common. So you will get then 1 plus 2x, and then this denominator. Okay. Now this x and this x cancels out. So what you are left with is this thing, limit x tends to 0 minus 1 divided by x 1 plus 2x square root of 1 plus 2x plus square root of 1 plus 3x. Now we have reduced our expression to this form. Okay, we started with this expression. We started with this expression, and we have reduced our expression to this. Okay, so again we use the facts of limit that I just uh, that we just used before. So I will use those facts only. So but now again we need to check that whether the limit of the denominator is non-zero or not in order to apply those facts. So limit of x tends to 0 of 1 plus 2x square root of 1 plus 2x plus square root of 1 plus 3x. Again, this limit can be broken into three parts by finding out the limit of this, limit of 1 plus 2x limit of 1 plus 3x. So yeah, so so limit of this first function will be a 1. Again, second function limit will again be 1, and in this case again it will be 1. So it will be 3. It will be 2 will be the limit of this thing, and the answer will be minus half. Okay. So this is an interesting problem. This question which you are seeing right now is an interesting question because one of the limit will exist and another limit will not exist. Okay, and you will see why that will happen. So I hope that all of you are familiar with the sine function. Okay, and what we are doing in this case, we are uh, we're making some changes in the sine function uh, when it hits the neighborhood of 0. So it's not the usual sine function which you see, because it is being composed with 1 over x square, pre-composed with 1 over x square. So sine function looks like, okay, so sine function looks like this. Um, okay, but the function that we are considering in here, so this function, first of all, just understand the behavior of this function 1 over x square. So 1 over x square function, as you go closer to 0, okay, so there are two ways to approach 0. So you can approach from left hand side, you can approach from right hand side. uh, you can approach from right hand side, you can approach from left hand side. So there are two ways to approach 0 in the real axis, x in the x-axis. So either way, wherever I approach, 1 over x square function will be tending to um, yeah, this function will be tending to infinity. Okay, so this function graph will go as you tend, as you go near to 0. Okay, so this function will behave like this kind of thing as you go near 0. Okay, so what happens that it is taking in a very small neighborhood of 0. Okay, it is taking almost all values of real line. Okay, positive real line, it is taking almost all values of positive real line. So that's what uh, make this sine function behave very differently from the one you are seeing on the left hand side. So what I'm saying is, whatever sine function you have for whole real line, that behavior excuses to this small neighborhood of 0. Okay, so whatever function, so you can, so on the right hand side, on the left hand side, we have sine function spread all over the real axis. Now think of that, you are excusing that sine function on the real axis to the to a very small neighborhood of 0. Okay, and closer you go, that denseness of the function is higher. Okay, I hope I hope you are able to understand what I'm trying to say. So what happens is, so this function graph will look like this. Let me draw that. Okay. So the function graph, I cannot even draw that. Um, it's very tricky. So let me try something. So it will be very dense, and it will be very dense near the zero, and then it will be start behaving like a normal function as you go. Uh, what I'm saying, I can understand no Desmos. Can you repeat what you are trying to say, Ravi? So my drawing might be looking like a uh, yeah, you can use online platform to draw the graphs. That's completely fine. I hope you are referring to that only. Uh, yeah, you can use either of that. That will be much easier for you to understand. So I'm trying to draw it by my hand. I'm just trying to give you the intuitive idea how will the graph will look like. So you can use whatever software you like to draw the graph. That's completely fine uh, with me. Okay, so you can see that this function sine 1 over x square function, this kind of like, this is a schematic diagram for sine 1 over x square function. Okay, so this function will look like this as you go near to zero. In a very small neighborhood of this, it is very dense. It is very uh, dense. Yeah. So yeah, now the question is, determine whether the following limits exist when x tends to zero. Okay, so a part is, you need to find out the limit of sine 1 over x square. Okay, uh, when x is non-zero. So so you need to find out this limit when x is non-zero. So clearly uh, this limit doesn't exist, because you can see that as x tends to zero, there are a lot of sequences you can find out which are converging to every value of, okay, so they are converging on the whole set, this thing. So as x tends to zero, this sine function is converging to the whole set of pi, minus pi to pi, sorry, minus 1 to 1. Okay, so what do I mean by that? It is not converging sequence. It is basically, it is not converging to a it is not converging at all. Okay, it's not converging sequence. So you can find it is going very near to the y-axis, but it's not converging to one particular value. So it's not converging. So this function doesn't have any limit as x tends to zero. Okay, yeah, but if I change this function a bit, it start getting a limit point at x tends to zero. Okay, so in other words, it will, you can have a continuous extension of this limit point. So basically this function is discontinuous. It is continuous everywhere else. It is discontinuous at origin, and this continuity is not removable type of discontinuity. It is not removable discontinuity. But the function that I'm gonna talk about next, which is uh, this function limit of x tends to zero of sine, this function, this has a limit This has a limit which is, yeah. So this has a limit which is, just a second. Okay. So this has a limit. So this has a discontinuity which is removable. You can define function at origin. Okay. So how do we see that? So we all know that sine 1 over x square, irrespective of what value you take, it will always be bounded by minus 1 and 1. Correct. And now you can further, so this function, this x times sine 1 over x square, this function will be bounded by, sir, when do we say that removable or not removable? So okay, so in this case, I will tell you when we can say that. So in this case, there is no limit to uh, to this function. Okay, you can see that this sine 1 over x square is converging to the whole of the interval, whole interval, minus 1, 2 plus 1. Okay, so it is not, so there is no a point which you can say that that you can define on where this function. Okay, you can define it to be that this will be the function, this will be the continuation of the function. So it is not a removable discontinuity. But in this case, you can this is, in this case you can say that you can define the function to be zero at zero, and you can say that this has a discontinuity, removable discontinuity. Um, yeah. So I can give you another example which is much simpler to understand. So I will give you that example of removable discontinuity and not removable discontinuity after this. So there was no need to go into that part whenever I explained this. Um, yeah. So in this case, I will use a result which is called as Q's theorem. Okay. So it says that again, in the case of limit, also we had Sandwich theorem. In this case, we have Skews theorem. So it says that if a function is bounded by uh, two function GA and HX, and uh, HX and GX, and limit of HX as A tends to X, and limit of GX as X tends to A are B, then limit of Fx as A tends to X tends to A is also B. Okay. So if a function is bounded by another function, and it bounds another function, okay, if it bounds another function, and the limit of both of the upper bound function and lower bound function is given to be the same as x tends to the same value A, then the limit of the middle function as x tends to A is also the same. So that's what the statement of Skews theorem. Okay, so I will use this theorem to prove that the limit of x times sine 1 over x square is 0. Okay, so it is bounded, so you will get this inequality from this property of sine x. So you will get, so that's the x sine, so this function x times sine 1 over x square is upper bounded by x and lower bounded by minus x. Now what happens to, so in our theorem, um, so in our theorem, gx is x. So in our case, gx is x and hx is minus x. Okay. So what is the limit of gx as x tends to 0? It is 0. Similarly, limit of x of hx when x tends to 0 is 0. Okay. So this implies by Skews theorem. So by Skews theorem, Skews theorem, that limit of x tends to 0 of fx is also 0. Okay, so yeah, so this completes the proof of this part. Now, what I yeah, so removal, discontinuity, and continuity. So I haven't discussed the continuity yet. Um, so I will discuss those concepts later when I will be having questions on continuity. Um, right now, I don't think it's a good time to discuss. Okay, but I can give you an example which I was thinking to give you. So, for example, you have a function like, so I'm directly drawing the graph of the function. Okay, so let's say you have this function. Okay, so this function is like it is constant up to if I write the definition of this function, so this function is let's say 1. Just yeah. So this function is 1 for x in this open interval. It is 2 at x equal to what is that? 2 at x equal to 0, and it is and then it is what it is, function which is x plus 1. Yeah, so it is x plus 1 function when x is from 0 to infinity. Okay, so what happens that it is having a jump. So this is 2, this is 1. So it is defined to be have it is having a jump. um, yeah, so it is having a jump on yeah, so it is having a jump at origin 0. Okay, until origin it is continuous, after origin it is continuous. So but at origin it is having a jump, so such things are called jump discontinuity. Okay, um yeah, so in this case you cannot uh, make it continuous because it has already been defined on x equal to 0. But suppose if it is not defined on x equal to 0, so let's take the another case when your gx is like this, similar to what we had, but except at x equal to 0 there is nothing being defined. Okay, so your function is like this. So this function is also not continuous at origin. Okay, so limit of gx as x to 0 is not equal to g of 0, so it is not continuous at 0. So not continuous at 0. So this kind of discontinuity, so it is discontinuous at 0, so this kind of discontinuity is called removable discontinuity. Why it is removable? Because you can remove this discontinuity, okay, by defining your function the limit of gx. Okay, so you can define this function to be 1 at x equal to 0. Okay, so this function will become continuous function if you define it this way. So this is removable discontinuity because you can, because the discontinuity is removable. Okay, so you can, once you remove the discontinuity, no, g at 0 is not known. Okay, but you can define g at 0. So how do you define g at 0? You can define g at 0 to be So you can define g at 0 to be the limit of gx as x tends to 0. So you can define g of 0 to be this. And this limit is well defined because this limit is nothing but 1. Okay, this limit exists, so you can define all this. You need to have the limit to be existing, otherwise you can't define. So this kind of discontinuity is called removable discontinuity, and the other one is jump discontinuity. Jump discontinuity can't be defined. Removable discontinuity can be defined. There is another jump discontinuity. This is yeah this yeah. So I hope it's clear to you what I am trying to say. Okay, good. Now we can move on to discuss these questions on limit. Okay, so what I will do, I'm not going to discuss these questions right now. I will discuss these questions in the next discussion session. So let's move on to discuss some questions which involve some theory part. Okay, so let me discuss these questions with you in the remaining 45 minutes. I will discuss these questions with you. Those limit questions I will discuss in the next uh, session next Monday. Okay. So let x be a sequence and L be a real number such that the absolute value converges to the absolute value of L. Then does xn also converges to L? So I will pause for a minute. I will ask you whether this is true or false. Okay. So what do you guys think that this statement is false? What do you think that is it false or is it true? Not always true. Which means false. It is false. Whenever you have like not always case, then it is false. Because in mathematics, whenever we say something, unless it's mentioned, we assume it to be true for all cases. So it is false. Okay. So now my so now in mathematics, whenever you say something is false and whenever you say something is true, you need to come up with a justification to that. So if you are saying it is false, you need to give me an example of a sequence xn such that number one, its absolute value converges to something, but the sequence doesn't converge. Okay, and if you are saying that it is true, then you need to uh, give me an argument to prove that. So okay, so yeah, so since one of you have said that it's false, can you think of an example uh, of a sequence for which these two conditions are being satisfied? It's a very simple example. I can assure you that. Uh, like the at least the one I know, it's very simple. So I think you must also be thinking of the same example. That's what I'm thinking. I will give you a few minutes. I will give you a minute to think. Others can also answer if they know. Okay. So so the answer is false. Okay, so you guys have correctly uh, found out that it's false. And the example that I have in mind is, yeah, so that is correct. So something like alternate, you are thinking that you are on where you are on, you are on correct path. So yeah, alternating sequence, correct. That completely makes sense. So what kind of alternating sequence that I'm going to take? So let's take, consider this sequence xn, which is plus 1 when n is even, and minus 1 when n is odd. Okay, so uh, what happens when you take modulus of this sequence? So modulus sequence is always 1 for all n. Okay, for all n in natural numbers. So modulus sequence is always 1. So it will converge. So this sequence will converge to its limit, which is 1. So this will always converge to 1. But this sequence does not converge. Okay, this sequence doesn't converge. So yeah, because there are two subsequences. And how do we prove that this doesn't converge? Because uh, you can consider of this sequence, which is x and 1, think considering all ones only. So you can construct two subsequences of this. One is consist of all plus 1, and another consists of only minus ones. And now these two are uh, constant sequence. Each one of subsequence is a constant sequence. A first one converges to 1, second one converges to minus 1. Okay, so it okay. Now how do we go from this? So now there is a result in sequences, which I will say. So if a sequence xn converges to a as n tends to infinity, then all subsequences of xn converges to also converges to a. Okay, so how do we prove that? The proof is very simple actually. um, does anyone know this fact, that what I'm writing right now? So let me start with the subsequence yn of xn. Okay, so I need to find, for every epsilon I need to find out some n. Okay, uh, such that yn minus a has to be smaller than epsilon. Okay, but for all n greater than equal to, but this is already true because xn converges to something, so xn converges to a. Okay, so that means what? So for this same epsilon, there is already an n naught in n, such that xn minus a is smaller than epsilon for all n in n. So for some sequences, for all, because yn is a subsequence of this, so after that n, all yn will also be satisfied. This all yn minus a will also be smaller than x, also be smaller than epsilon. So this is trivial from this fact. So any subsequence of a converging sequence also converges to the same limit point that we had. Now, how does it useful in this question? Okay, you haven't got this. So I think till this part it is fine. That xn converges to a, which means that for epsilon greater than 0, there exists some n naught such that this happens. Okay. Now for sequence yn, you need to find out some n, correct? So you can take this similar n naught. So you can take n to be n naught. Okay. Take n to be n naught. So now yn is a subsequence of xn. So yn already satisfies this condition. Hence proof. Is it fine now? Okay, thank you. Um, so um, yeah. So what we had here. So yeah. So if xn, yeah, we were trying to prove that xn doesn't converges, okay, to anything, and we have found out two sequences which is converging to two different values is -1 and +1. So this basically contradicts to the fact. So if we start assuming that xn converges to something, then its subsequence must also converge to the same value. Okay. Uh, so, but we have found out two subsequences which are converging to two different values. Two different values. So this implies that xn must not converge. Okay, which is kind of like a contra-positive statement of this. If subsequences converges to different values, then the original sequence must not converge. Okay. Yeah. So that's what we are using. So here xn2 is a subsequence of xn1. No, is it? It's not. xn1 and xn2 are subsequence of xn. So xn1 and xn2 are subsequence of xn. And if you assume that xn converges to, let's say, 1, then there is a sequence xn2 which converges to -1, which is a subsequence of xn. So it contradicts to this fact. Okay. And if you assume that xn converges to -1, so there is xn1 which converges to +1. So it again contradicts to this fact. Okay. So in either cases, the limit doesn't exist of xn. Okay. This implying that xn, limit of xn does not exist. Okay. Um. Yeah. Okay. Now I also want to discuss a few things in this question because this question is interesting. Okay. So we have proven that uh, that it is a false statement. Number one thing, we have also given an example of a sequence whose absolute value sequence converges, but uh, the sequence or the sequence doesn't converge. Okay. So now what can we say about the absolute? So about the relation between absolute value sequence and the sequence. So basically, so what do I mean by that? So we have seen that if the absolute value sequence converges to something, it doesn't imply that the ordinal sequence also converges to the same thing. Okay. So we have seen that if ordinal sequence, if the sequence, absolute value sequence converges something, then the ordinal sequence need not to converge to that thing. Okay. But can we, so now the question is, can we say the otherwise also. Does the otherwise, the vice versa of this thing, make sense? Which is, if xn converges to something L, okay, if I have a sequence which converges to L, then does absolute value of xn converges to this? Okay, does the absolute value of xn converges to L? So the answer is yes, and the proof is very simple. Okay, so how do we prove that? So we use the fact that, xn converges to L. What does this mean? That for given epsilon, there exists n in natural number such that xn minus L must be smaller than epsilon for all n in natural numbers. Correct? Yeah. So now what? In order to prove that xn modulus of xn converges to modulus of L, what do I need to prove? That for this epsilon only, for the given epsilon, I need to find out n naught in natural numbers such that mod of xn minus mod of L, this thing is smaller than epsilon for all n greater than equal to n naught. Okay, so how do we find that n naught? So we find, so we use something which is called triangle inequality. Okay, um, so triangle inequality, what does the triangle inequality says? That summation of two values is two reals. If you take my modulus of that, it is smaller than summation of the individual values. Modulus of summation of individual values. Okay, yeah. So in this case, for all a b in real numbers, so in this case, how do we use this? So we take a to be xn, yeah, we take a to be xn minus L, we take b to be L. Okay, so if you take these values, what will you get? You will get xn minus L plus L is smaller than or equal to xn minus L modulus plus L. Okay, which is equivalent to say that xn modulus minus L, you take this L here, is smaller than this thing, and now this value is smaller than this value, so its modulus will also be smaller than. So this whole modulus will be smaller than this modulus, which is nothing but this. So you have got a bound on the absolute value sequence by the ordinal sequence. Okay. Now we use this. So let's call this A. So we use this part. Oh, um, okay. So now from this part, I will get, what do I get? I get a bound on xn minus L smaller than epsilon for all n greater than equal to n. So my n naught is nothing but going to be n only. Okay, because I have bounded this thing by the ordinal sequence, and for ordinal sequence, the n was the number which gives us the bound. So I will take my n naught to be equal to n. So the converse part is true. That's what I try to emphasize on. The converse part is true. Okay. let's move on to discuss this question on uniform continuity. So I will start with the definition of uniform continuity and then I will prove this result as well. Okay, so question number two. So we have f to be a function from R to R. It is given to be a continuous function. Okay, and A and B are two non-empty sets. So they are two non-empty subsets of R. And further, you assume that f is a uniformly continuous function on A and on B. Now the question is, what can you say about uh, the uniform continuity on their union? So let us first recall what is a uniform continuity means. What does the uniform continuity means? So we say a real valued function on real variable f is a uniform continuous on some domain A if for every epsilon greater than 0 there is a delta only depending on epsilon. Okay, only depending on epsilon delta such that fx minus fy is smaller than epsilon whenever x minus y is smaller than delta. Okay, so this delta has so this delta only depends on the epsilon. It doesn't depend on the point that you are choosing. Likewise in the continuity case. Okay, so this is the uniform continuity. Okay, so after recalling the definition, let us come back to the question. Now we have given in this question that f is uniformly continuous on A, f is uniformly continuous on B. Now, what about on A union B? Okay, so so what do we need to prove? We need to prove that for given any epsilon, we need to find out a delta such that this thing is satisfied. It is also union C. No, it is only to A union B. There are only two sets involved. Okay, so um, so let us just write the definition of uniform continuity in both of the cases. So for a set A, okay, so because f is a function uniform continuous on A, so on A I will get for every epsilon, I will get some delta epsilon. Okay, so I will call that delta epsilon to be delta epsilon A. Okay, just to refer that it belongs to uniform continuity on A. Similarly, this when f is uniform continuous on B, I will get for the similar epsilon. I fix my epsilon. I have I have gotten this epsilon delta epsilon A. Okay. Now for B, I will get another. I will get another this delta. Okay. Now I can choose. Now these are two real values only. Okay, these are two real numbers. I can choose the minimum of that. and I will call that minimum to be delta. Okay, delta epsilon, because epsilon may depend, it depends on epsilon, so it is important to write, it's important to keep track of epsilon. Okay, so I have gotten an epsilon delta epsilon. So now I use this epsilon delta. So for epsilon greater than 0, I have found out epsilon delta which is greater than 0. So there exists epsilon delta such that fx minus fy is smaller than epsilon whenever x minus y is smaller than delta on AB. Okay, now there is a thing to check. So suppose it is not to check, it is just to verify that whether we have done the same thing, correct thing or not. So if your x, y belongs to A, okay, so you already have some, so there is no delta B, so there is no delta B. Okay, so your delta will be then the original epsilon delta A. Similarly, if both of the elements belongs to B, then it is going to be this, and if they belongs in the intersection, then your delta will be the minimum one by definition that we have just taken. So basically this definition, this choice of delta covers all the possibilities. Okay, so this proves that your function is uniform continuous on A union B. Okay, so this completes the, yeah, so this is the last step of choice of delta. So this is what I'm choosing a delta to be the minimum of the first one and the second one. In each of the case, I get some delta depending on epsilon for A and for B. I take the minimum of those. Whenever required, I will take the minimum of those. That's how I'm taking the delta. No, intersection is not minimum. How can you take intersection to be minimum? You just take the smaller. Okay, I might have confused you when I was talking here. So just forgot about this thing. Okay, so this is not important. This is this doesn't make sense. Okay, so you have, so for a given epsilon, you have some epsilon delta, which is nothing but the minimum of this thing. Okay, just that's all. This is the proof of uniform continuity. So if you, so let's say if you take an element x and y which is in A but not in B. Okay, if you consider such a set, because A and B are like these two sets. Okay, think of like Venn diagram. So this is A, this is B. So there will be some elements in which are not in the complement, which is in the B complement. Okay, so there will be some elements which will be in A, which will be A intersection B complement. So you, for that, your delta is already smaller. Okay, so this thing will already be true. Okay, so this delta is already is, yeah, it is already be smaller. So this delta is already smaller than this thing. Okay, so in this it will always be, you are taking a smaller range, you are taking a smaller neighborhood of uh, a set. Okay, so you are taking a smaller interval. So this will always be true. Similarly, when your x and y will be in this intersection, again this thing will be true because this is smaller than your beta epsilon, because you are taking the minimum of either of that. So this will always be true. And in case of intersection, it is already true because you are taking anyway the intersection. So anyway you are taking the if you take any point in the intersection, this will be true because you are taking the minimum of each of the delta. So this is smaller than this as well as smaller than this. So you are done. So this basically includes all the cases, and your this proves that f is uniform continuous on a union b as well. If it is uniformly continuous on a and uniformly continuous on b. I hope it's clear. uh, I think we can move ahead to the discussed last question of today. I hope last question. Yeah. So this will be the last question. Okay. So you have given two continuous functions f and g. You need to say that the maximum of f and g and minimum of f and g are continuous. So let me first start with recalling the definition of continuous function, because you guys haven't seen the definition of continuous function in my discussion session. So let me just recall that. So we say a function f, real value function f, or on real variable, uh, to be continuous at a point x. Take another point. Some take, let's say, take b. Okay, at b, if for every epsilon greater than 0, there exists some delta greater than 0, such that fx minus uh, fb is smaller than epsilon for all okay. So let me write it more um, thoroughly. So it is said to be continuous at b if number one, um, f has a limit at b, okay, and second, the limit of f fx as x tends to b is equal to f of b. Okay, so this is more appropriate definition. Okay, so if I combinedly write these two things, what does it say? It is equivalent to say that for every epsilon greater than 0, there exists delta greater than 0, such that f of x minus f of b is smaller than epsilon uh, whenever x minus b is smaller than delta. Yeah, so this is my b is same actually everywhere. It is, yeah, this is better. Okay, I hope it's fine. So b is same. Yeah. So this is the definition of f being continuous at a point, and we say it is a continuous function. Okay, so we say f is continuous on R if it is continuous if f is continuous on each point x in R. Okay, so this is the definition of f being continuous on a domain. Okay, so this being said, let's come back to this question now. So we have given two continuous function f and g. You need to find out you need to say that their maximum is also continuous and their minimum is also continuous. So I will leave this question with few exercises. I will leave to you guys to do that exercise. Okay. So now maximum of f and g. So maximum of f and g. So this function can be defined algebraically in terms of f and g. Okay. So it can be defined as fx plus gx by 2. Okay. Yeah. Plus modulus of fx minus gx by 2. Okay. And minimum function. Okay, so let me give you explanation why does this definition make sense. So this is, suppose this is your real line. Okay, what does it mean? um so you call this function to be hx. Okay, so it means that um, fx, if fx is greater than gx. Okay, and gx if gx is larger than fx. Okay, so this is the maximum function. And minimum function of f and g can be defined as, let's say this function I am calling it to be h p of x. Okay, so p of x, or better notation will be capital M and small m. So maximum with capital M, this with small m. Yeah, so it is fx if fx is smaller than gx, gx if gx is smaller than fx. Okay, so this is how we define. And what I'm saying is that you can write this function, you can write uh, mx as this thing. Similarly, you can write mx, maximum function of f and g, in term algebraically in terms of fx and gx. And how do we do that? We do that in this way. Now, how do we allow a justification to what I'm saying is this? Let's say this is your fx. Okay, let's say this is your gx, and let's say this is your fx. Clearly, fx is larger than gx. So, what should be the value? Value should be fx of mx. Correct. Now, if you take the first term is saying the average of first two values. Okay, average of fx and gx. So yeah, so if you so what will be the average of these two values is, so it will be lying in the middle of this thing. So this point will be fx plus gx by 2. This is that point. Correct. And now in the second term you are taking difference, you are taking the absolute value, absolute difference between fx and gx. So that absolute difference measures length of this interval. Okay, so this absolute difference measures the length of this interval, which is gx comma fx. Okay, so you get this distance. Now if you take the half of the distance, that distance, half of this will be this distance. I'm saying distance. Okay, half of that will be this distance, correct? And now you are adding this distance to this midpoint. What will you get? You will get fx, which is the larger value, correct? And if you substitute this distance from the midpoint, you will get the smaller value, correct? So this is how that is how we define. So the mx also, small mx also. So mx will be defined first the midpoint of the both of the points. Okay, subtract the distance of half of the distance of fx minus gx. Okay, so this is mx, this is capital Mx, this is small mx, maximum function, minimum function. Okay, so I have written down expression of maximum function and minimum function in terms of f and g only. Okay, so now once you have this expression, I leave a few things as exercise to you. Exercise number 1, sum of two continuous function. Okay, so show that f and g is continuous. Okay, fx plus define hx is nothing but fx plus gx, then hx is continuous. Proof is simple. Okay, you can refer to any standard textbooks also, you can find it. Now another exercise for you is that hx by 2 is also a continuous function. Yes, yeah, so those function will also be continuous. Okay, now third exercise is composition of two functions of two continuous function is again continuous. So what do I mean by that? If h1 and h2 are continuous function, uh, such that h1 range of h1 is contained in the domain of h2. Okay, do we say that? Basically h1 is from r to r, and h2 is like this. So h2 composed with h1x, which is defined to be, is also continuous. Okay, and fact that modulus of modulus function, which is fx defined to be modulus of x, is continuous. Okay, you can prove this also. This is also simpler exercise. Okay, just prove it. This is continuous. This is another exercise. Exercise number 4. And now using these 4 exercises, okay, now using these 4 exercises that I just wrote, you can the break first expression. So this first expression is so this first part become continuous. Okay, now second part, which is now this function is also become continuous. Fx minus gx is also continuous. Now if you take compose it with the absolute value function, this is again continuous function. Divided by 2, it is also continuous function. Now summation of these two continuous function is again continuous function, proving that this function is continuous. Similarly, fx plus gx by 2 is continuous. Subtraction with this thing is again going to be continuous. So the small x is also continuous function. So that means we have proved that maximum of fg and minimum of fg are continuous functions. Okay, so this statement is true. So these are the four exercises that I'm leaving for you guys to do that, and using these four exercises you can, yeah, composition of continuity you can prove. You can find it in extended text also, and if you are not able to do it, I will explain it in the next session because today's time is over, so I will do it in the next session. The composition of continuity you try. If it is not clear to you, you can ask doubt on that to me in the next session next week. Okay, so using these four exercises you can prove uh, that this expression, these two expressions are continuous, and these two expressions are nothing but expressions of maximum and minimum functions. So in other words, the maximum and minimum of two continuous functions is again continuous. So this completes the proof of this question. So I stop here. uh, so if you have any doubt, you can ask me in the next session, which I'm going to take next Monday, 7 to 9, same time, same link. A recording of this session will be available on my YouTube channel, Maths with Prerak, Prerak Deep. You can go to that channel and you can find a link um, to these recordings. So I will upload this recording of today's session by tomorrow. Okay.